All right. I'm going to show you the refinement of some of the ideas we've been showing you for a while, as they now are likely to look in actually in version 14. So the first thing is I've shown you that FGH implements forks, and a lot of you have already seen this stuff. I'll show you a couple of examples. This is an idea that came from Roger's work in Jay and Ken's work. So this is an example of a monadic fork. This is the average function coded as a fork. So there are three functions here. There's summation, division, and shape. We can name the fork, and here we can apply a named fork. So these have made it into the list for 14.0. They will be there. Here is a dyadic fork. So you can see from the... Is this working? Yeah. You can see from the definitions, this just tells you the definition that alpha FGH omega is the alpha F omega and alpha H omega with a dyadic G between them. So we can see a dyadic fork there. Most of you have seen this before, but there are some things that have been toned down a bit. And we will be producing longer trains as well. So a fork is an odd number of functions in isolation. And you can see this example is 6 and 2 plus, comma, divide, comma, product, comma, quotient. And there's no magic there. That's just an application of the three trains as forks that we've been showing for a while. Showed you this in Boston. In Boston, we were experimenting with a lot of other flavors of fork. Oh, sorry, and this is one more. If A is an array, then the form AFG is shorthand for this function, the three-function fork, where this function effectively ignores its arguments and just returns the array. So, for example, this function would return the 2 reshape of 3 and 10 and the product of those two things. But in this version, we'll be able to spell it like this. So effectively, this function in the middle is the 10 times the 2 reshape 3. And here's a monadic example. So this is just a summary of the 3 train definitions. There's a monadic case, a dyadic case, the FGH case, and the array GH case. And this is what we will be implementing. In this release, there will be no 2 trains. And even trains will generate a syntax error. So we won't have hooks, we'll have only forks. And I think, as I've said elsewhere, these are quite easy to hooks are quite easy to emulate in Dyalog anyway. And we're keeping that syntax reserved for the moment. So that's hooks. Forks. That's forks. Right, thank you. Okay. The next thing that will make it, of all of these ideas into the 14 release, are right operand currying for dyadic operators. For example, the power operator is a dyadic operator. It takes a left operand and a right operand. And if you omit the left operand, then it derives a monadic operator. So in this case, power neg1 derives an inverse operator. So for instance, if I have a next function, so where the next of 2 is 3, then next inverse of 3 is 2. So this is just the inverse operator takes a function and produces its inverse. This is just right operand currying. And another example of this, also with power, is power limit, which is until there's a match. So this will do for instance, this is an expression where this function is applied repeatedly, plus the reciprocal of, until the argument and result are the same. So this is so we have these are examples: an inverse, and a general fixed point operator can be just assigned a name. And the last thing I want to show you before I hand over to Roger is there will be a new primitive operator. You can't really see that, but it's a right arrow inside a box, and it's we only have a model for this at present in this workspace, and it's a merge or amend operator. So if I copy the model in, and in fact it's a dyadic operator, I'm just going to in the model. This right operand is used to specify axes, but I don't need that in this demonstration. And the primitive operator will be a monadic operator, so I can just name a monadic version of this. So if I make, for instance, a matrix of numbers, then there are two cases of this merge. The first case is with indices as operand. So what this is saying is this merge operator, which will actually be spelt box arrow, says this matrix, but with these values at these positions. So it's a sort of triadic operator. You've got a starting value and a replacement value and a specification of where to do the replacement. And it's equivalent to, it's modeled on the squad indexing. So this is equivalent to, but nicer than, this expression, where this you can put in a stream of code, whereas this you have to do squad indexing, you have to name the array, do a selective specification on the array, and then you're left with a name which you may want to expunge afterwards. Whereas this is it will be a lot slicker. That's the first case. And and the conformability conditions as are per squish, so that in this case I'm merging a 2x2 array at these positions in a larger array. And the second case is with a Boolean selection function. This case had the operand was an array, but if I give a function as the operand, then what this does is a function which identifies, it makes a Boolean mask. So this is merging at numbers that are multiples of 3, so 12 and 15, 21. So it's putting a 0 everywhere this condition is true. And the above merge is... I think it probably is, yeah. Okay. And this is, again, is equivalent to but nicer than this expression. They're just they're a more functional approach. You don't have to do an assignment or find a name. So the conformability for these will be as per Ravel, as we saw here. So we're putting 7 items into these 7 slots in this array. There could be some tweaks on these definitions, but broadly, that's what that's the new. So this is the summary of my part of this. We'll be doing forks but no hooks, left operand currying, and a primitive merge operator. Okay, so over to Roger.
So my name is Roger Hui. Given what's been said this morning about snakes, let me point out that both Gitta and I were born in the year of the snake. And according to the Chinese, snake people are wise. So I'm going to talk about 4 potential version 14 language features. They're all taken from J. It just means that they have had about 20 years of use. So the first one is the rank operator as both a monadic and a dyadic case, and some examples of its use. So what's it good for? Suppose you have a program or a function that can do something like sorting. Or then using the rank operator, you can apply the function to subarrays of an array. So in this case, it's sorted each row of the three-dimensional array. And if you use enclose as the function, then it gives you a clear picture of what's going on. So in the first example, it's doing enclose rank 2 or enclose the matrices of the argument. And in the second example, it's enclosing the vectors of the argument. There are dyadic uses of rank as well. So in the first example, I'm adding scalars in the left argument to vectors on the right argument. So the 10 is added to the first row of the right argument, the 20 to the second row, and the 30 to the third row. And in the dyadic case, if you use link as the function, in the curly brace, the alpha and omega juxtaposed means link. And you see that the scalars in the left argument are linked to the vectors in the right argument. Left rank 0 and right rank 1. The next potential language feature is the key operator. You have two arrays X and Y, and the cells or the subarrays on the leading dimension specify keys for the corresponding cells on the right argument. And then you apply F to each collection of Y having the same keys. It's like the group by concept in SQL. And in the monadic case, the only argument or the right argument are still the keys, but they would be applied to indices. Professor Filimsky mentioned the connection machine this morning. I got the idea for the key operator by reading the manual for the connection machine in the 1980s. So, if a concept is good enough to be implemented in hardware, it's a concept that's worth stealing. So here's an example. I hope the colors are visible. Anyway, X are a character matrix of keys, and Y are corresponding data. So if I say X enclose key Y, it encloses the data that have the same keys. So all the IBMs got put together, and all the Apples, and the Googles, and then the Microsoft. Okay? And if you use a different function such as summation, then it still does the grouping, but apply the function to the groups, and in this case you get the group sums. The monadic use. So if you say, remember now, X are still the keys, but the data items are simply the indices, the cell indices. So here I have the group indices. So in other words, rows 0, 6, 9 are the IBMs, rows 1, 4, 7, 8 are the Apples, and then 2 and 3 are Google, and 5 is Microsoft. And if you supply a different function, in this case the first element of the shape, you get group counts. So there's 3 IBMs, 4 Apples, 2 Googles, and 1 Microsoft. I think if you like segmented scans, you should like this. And I expect that by the end of the talk, you would have a vectorized version of this. So the next feature is called tally. I'm sorry. Question. Phil asked.
The key operand is apparently always monadic.
Key operand.
Yeah.
Yes.
It struck me that in a lot of cases you might want access to the key that produced the group. So, for instance, where you've got a 3 there,
yeah,
it's allied to IBM. The 2
Yeah.
is allied to Google.
Yeah.
Is there any way that you could write it such that that was available as a left argument
Yeah.
if you...
Yeah. I have thought of that. I think having a monadic, applying the operand function monadically makes the use simpler, but it doesn't reduce the generality. By writing the function appropriately, you can actually get what you ask for, both the... I guess not.
You've lost
Well, anyway,
by that time.
it complicates the common uses of it too much. I think once you have the group indices, you can then, pick out the keys if you needed them.
Runs once on the group.
I'm sorry? Yes, once.
In that instance, the function will only run 4 times.
Yeah.
So is there any difficulty in supplying it as an optional alpha? Sorry. Would there be any difficulty in supplying the key as an optional alpha, which you might ignore anyway?
Well, except, what do you do with this? I want the
Because
group
that
sums.
is self-ambivalent. You've got a problem, yeah.
Yeah.
All right.
So I don't want to complicate these kinds of uses with the dyadic case, which which you only want seldom, I believe. Okay. But good question. So tally is just the length of the leading axis as a scalar, which you in APL have needed all these years, but you just didn't know it. And why do you need it? Well, some examples, the tally of tally of X, this character matrix is 10, which is the number of rows, and the tally of a scalar is 1. And if you say tally key X, it gives you the group counts, which is a bit simpler than what I said before because the function is simpler. And this is the way the average function should be written. Well, because the average function returns a wrong rank answer. It returns a vector instead of a scalar. And I saw this in some code I was looking at just last week. I myself don't care for strand notation, but many people do. And if you have, C is a vector and I want to make it into a 2-column matrix. So, and I know the number of elements is even. So a natural thing to do is say I want to find the length of C divided by 2 and strand the argument to reshape, and you get domain error. But if you had tally, it would just work. It's actually one of these amazing things, because Arthur Whitney has this as a primitive in K, and to him, if you know a little bit about K, symbols are very, very precious resource to him. He only has single character primitives, and he uses only single letter ASCII letters for primitives. And yet he has tally as a primitive. It's more useful than it first appears. Okay, the last possible version 14 feature is an extension to index off. I won't try to explain the APL, except that here's immediately a good use of the rank operator. You see it's much shorter than the equivalent axis expression. Yes, and the question is, does it work in both origins? It does. It's a compatible extension to the current index of, and it's a generalization of the mat iota idiom that Dyalog has. So in the extended index of, if the left argument is a vector, as now you look for scalars. If the left argument is a matrix, you look for rows. If it's a three-dimensional array, you look for matrices, and so on. So why are we contemplating extending index of? Well, as I said, it's a generalization of mat iota. It's used in the definition of key, and it's a better tool of thought. And I'll give an example of the fact that it's a better tool of thought. Since the early days of APL, people have known that n dot equals is a very useful computation. And so many implementations have special code for n dot equals, in addition to the general inner product. So Sharp APL in the 1970s had special code for n dot equals. And likewise, Dyalog APL has special code for n dot equals. Well, I recently thought of a way to speed it up. And the way I thought of it was in the red, or now blue, in the red, with the extended definition of index of. And I would demonstrate the timing with mat iota. So I've generated a 800-row character matrix with 13 columns. And then B would be a 900-row character matrix with the same number of columns. And so F0 and F1 give the same results. In other words, A n dot equals, or alpha n dot equals transpose omega with the optimized special code gives the same result as this. But my APL expression with the mat iota, or the extended index of, is faster. And the advantage is still there if you add or subtract the time it takes to do the transpose. So, in 46 years of APL implementation, nobody thought to speed up n dot equals this way. And with the extended definition of index of, they might have thought of it sooner. Coffee time.